Hello, everyone. From yesterday, if you remember, we did a quick refresher on what we did in class a couple of weeks before, and at the end of the refresher, we talked about mappings. And mappings were a way to kind of convert let's say, a two-dimensional space or a three-dimensional space into some other space where something that didn't used to be linearly separable, like this example here, became linearly separable. So we said that we'd have a function phi, call our mapping function. That's a bad phi. Uh, Function phi of some vector x in the original space would give us uh, some mapping that's in some other space of different dimension. And sometimes that number of dimensions in the mapped space would be much higher than the original space. And we said that you can do different things, like, say, for example, take the squares of the individual dimensions and make that a third dimension, and so on and so forth. It turns out that you don't actually have to do this mapping for every point. All you need is the relationship between the points. So if we Okay, so we define what's called a kernel function. So what the kernel function does is, instead of, and generally it's called k, it takes two vectors, let's say x and z. These could be, for example, two-dimensional vectors. X might be something like 2, 3, and z might be something like 1, 5. And k is defined as the dot product of the mappings of these two vectors to the space you want, or rather, if you're thinking in terms of matrices, the transpose of the first map vector times the second map vector. And usually, for example, in our cases where we looked at linear SVA, linear PCA, K was very simple. K was just uh, the dot product of x and z. And we'll see how that happens in a minute. But so essentially, the mapping of x was x itself. So we didn't do any mapping. The kernel was just the dot product. And now the idea is, and what we call the kernel trick in machine learning and pattern classification, is, instead of using x itself, or rather the dot product of two vectors x and z, we plug in the dot product of the mapped versions. So now the naive way to go about this is to take x and calculate its mapping, and then to take the other vector z and calculate its mapping, and then take the dot product. But it turns out that for most interesting kernels, it's much easier to calculate the product of the mappings directly, instead of calculating the mappings first and then taking the dot product. Uh, so here's an example. So here's one example. Assume you have this mapping that maps any vector from however many dimensions it has, for example, RD, to twice the number of dimensions, right? So from Euclidean space to Euclidean space with twice the number of dimensions. And here's the example for a three-dimensional version. And what it does is, if the vector is x and it has elements x1, x2, and x3, right? It takes each one and multiplies it with itself first, then it's the first one with the second one, the first one with the third one, and then the second one with the first one, second one, third one. So you can think of it like a double for loop, right? For I in range whatever number of dimensions, you can, and for j in range same number of dimensions, each element of the final matrix, let's call it F, the final vector would F would be let's say F append xi times xj. So it's easy to see that for a thing like this, it would take on squared time, right? So however many dimensions you have, if it's a three-dimensional case like this, you have 9 products to calculate. If it's four-dimensional, you have 16 products. If you have 5 dimensions, you have 25 products. So calculating this takes on the order of n squared time. The problem is you have to do this for another vector as well, right? Because if you're calculating k of x and z, let's say pen won't write. Let me see. Let's try this again. Okay, here we're calculating k of x and z. Just a minute. I seem to be having a problem with my pen. Okay, that's better. X to z, you have to calculate first the original mapping for the first vector and the second vector, and then take the dot product. The dot product basically says you take each one of these dimensions and the other for the same one for the other dimension and multiply them. Notice that what you're doing then is essentially multiplying something like this, right? You have the z of the same type, z1, 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 z2, and so on and so forth. The trick here is, though, if you look at the first kind of, when you're doing the dot product of these, you have to multiply this pair of this multiplication with that multiplication and add it to the sum, and then do that. And so for what you're doing is essentially x1, x1, z1, z1 plus x1, x2, z1, z2, x1, x3, z1, z3, and so on and so forth, in this case 9 times. Well, 6 more times. But now if you regroup these, you find something interesting. There's always, you can regroup them as products of xc. So this is the same as saying x1 z1 times x1 z1. Sorry. Let me just write it here. This is essentially equal to saying x1 times z1 and x1 times z1 again. And here, yeah, you can have x1 z1, x2 z2, and this one is x1 z1, x3 z3, and so on and so forth. So you notice that when you group them, you only have to calculate this once and then keep reusing it, and you have to only calculate this once, and so on and so forth. So you basically have to calculate x1 z1 product, x2 z2 product, and so on and so forth. So you just only have to calculate n products, and then it turns out you can just take this, you can just multiply them and take the square. So you basically only have to do n units of work, which means you can compute this in on time. That's what I mean by saying sometimes calculating the kernel, meaning calculating the this k directly, instead of calculating the mapping of the first vector first and the mapping of the second vector first and then calculating multiplying them, would be slower than calculating the kernel directly. And furthermore, there are other cases where, for example, in this case, our mapping was to a dimension double the original, but in other mappings, you'll see that actually you can map to an infinite dimensional space where it's really not possible to calculate the mapping itself, but it is possible to calculate the kernel, meaning the dot product of the mapped vectors without calculating the mapped vectors themselves. Okay. So here are some example kernels that get used fairly often. The first one is a polynomial kernel, so it's just like the dot product, but now it has a power of the dot product, so you can essentially model parabolic spaces, higher order spaces, etc. So, for example, if your data is something like this, you have your points here and other points like this of different classes. A linear model will not be able to really model this, but a parabolic thing can actually separate these. Or if you're doing clustering, we'll be able to show them as different clusters. Another kernel that gets used very often is what's called the radial basis function kernel. So essentially, when you think about it, the kernel is the mapping between the dot product of the mapping between two vectors is this exponential. Essentially, that's saying you're saying that the x and the similarity between x and z gets exponentially smaller as as the distance between the Euclidean distance between x and z gets smaller, because you're subtracting one vector from the other, taking the square, so this whole thing is essentially the Euclidean distance, and then you're dividing it by some spread, which, when you call it the Gaussian kernel, is actually kind of parametrized by sigma, the standard deviation. And then notice that if x and z are very close, this whole term is very close to zero, so the exponential is higher. But then if x and z are very different, the distance between them is very high, then this top part, the denominator of this fraction, is much higher, which means that the exponent of e is much higher negatively, meaning that the whole similarity would be much lower. So essentially, you can think of this as if x is here in the space, there's if it's, for example, one-dimensional, you essentially fit a Gaussian on top of x, and for example, if z is here somewhere, it has a higher similarity to x, but as it falls off towards the tails, it gets less and less similar. And you notice that in order for this e to the power minus something term to be equal to the multiplication of two vectors, each of which is essentially a mapping. Some of you will know this as kind of a Taylor series expansion. So each one of these would be an infinite series, meaning you can't actually calculate these mappings, but since they are infinite series that are diminishing series, you can actually calculate the sum of their products. So that's what I mean by sometimes you need to calculate the kernel directly and not do the mapping first and then calculate the kernel. Another example is the inverse multi-quadratic. So now the question is, can any function k be a kernel? Any function that takes two vectors and spits out a number, can it be a kernel? Intuitively speaking, since our most basic kernel, which is x dot z, x dot product z is a kernel, the linear kernel, and you have to figure out what this does. You know that the inner product, the dot product of two vectors, are essentially gives a projection of one vector on top of the other vector, right? So if these are x and z, let's say this is the one option for z. Essentially, this is the projection of z on x. So how you can think of it as how much along the way on x does z go. So if, for example, let's think of a z prime, which is very similar to x, you'd get a much higher positive number. And if it's pointing the other direction, you actually get a negative dot product. So the dot product is a function of the similarity of two vectors, right? So if it's zero, if they're orthogonal, it goes negative if they're pointing in different directions, and it will be the magnitude of the vectors if the vectors are coinciding. So if they're identical. So what this means is if you come up with any function that roughly gives the similarity of 2 points in your space, however elaborate it calculates them, it might serve as a vector. So one example from genetics and bioinformatics is one idea is maybe you can use the edit distance as a kernel, right? So obviously the inverse of a kernel. So if you have two DNA sequences, A, T, C, G, A, etc., and then another one, A, C, C, TCGA or something. Now you think of how do I convert this one to the second one? These might be your 2 points, right? So you can think of, for example, if I throw out this C, if I delete this nucleotide and if I mutate this into G, then with 2 edits I can make this identical to the original one. So it's an edit distance of 2. Another sequence might have a higher edit distance, which means on the kernel, it will have a lower value, and so you can kind of design a kernel to do this. The problem is kernels have to obey certain laws to be widely applicable. We'll talk about those laws more formally in a minute through Mercer's theorem, but you can think of it like this. In order to evaluate your function as a kernel, you can think of the function as a matrix. And as you know, by mathematical definition, a function is basically something that takes any value and maps it to some other value. So if you actually know all of your input values, you can pre-compute them, right? So if I know that this function is only going to take the values 1, 2, 3, 4, I can build a matrix, and let's say this function is taking 2 values, x and y, and each can only be 1, 2, 3, or 4. I can say, okay, 1, 2, 3, 4, 1, 2, 3, 4, and build the matrix such that each intersection is the function calculated for those 2 inputs. Hence, there is a duality, rather, a duality between matrices and functions. So for any function with a finite domain, you can actually create a finite matrix. For any function that has 2 arguments, you can calculate a finite matrix that has all the outputs of the function pre-computed. So if our kernel with 2 inputs has a finite number of inputs possible, which would be in our case our data set, you can actually calculate the kernel for it. So now we can use this kernel to figure out whether our kernel function obeys certain rules. So matrix is defined as each cell ij is the kernel function evaluated at the xith vector and the xjth vector, calculate the kernel and put in the value. Kind of intuitive way to think about it is, let's say your x's are different cities. Let's say you have 20 cities and you have a function that calculates the distance between cities. You can always make a matrix with the city names here, and each intersection is the distance of one city to the other, or in this case, the similarity of one city to the other. So when you think about it that way, it seems very obvious immediately that this kernel matrix has to be symmetric. Obviously, for example, going from Ankara to Istanbul, if it's a certain similarity, a certain distance, going from Istanbul to Ankara has to be the same distance, the same similarity. So, and you can think of it mathematically as well. Obviously, the dot product of a mapping of x and z should be equal to the mapping. Oh, there's a little problem on the slide here. So this is z, this is x. The mapping of x dot product z should be equal to the mapping of dot product z times x, since this is commutative. So it has to be symmetric. Somewhat less obvious is that this matrix has to be what we call positive semi-definite. In other words, when you kind of do the eigen decomposition, all the eigenvalues have to be greater than or equal to 0. If it's positive definite, they have to be greater than, actually strictly greater than 0. If it's semi-definite, they have to be 0 or higher. And you can think of it this way. Obviously, applying a function to matrix to vectors is the same thing as taking the first vector, multiplying with this matrix, and then multiplying with the second vector. Now assume we're using the same vector, so we're calculating kxx, right? Now this kxx, we know, for example, if somehow x is 0, 0, meaning its magnitude is 0, this will come out to be 0 if you take the dot product. If it's something else, let's say 1, 0, it will come out 1, because it will take the magnitude of the vector. The dot product of this thing with itself would be the magnitude. And it could be anything other than 0. But if you put x, and x, whatever x is, it can never be negative, right? Because that would mean you put x and you put the second vector x, which is identical. It's not pointing in the other direction, so it can't be negative. So remember with discussions of measures, we said that there's the constraint of self-similarity. Actually, self-similarity is not a good term here, because it also means something else in terms of self-similar shapes like fractals. But what I mean here is it's essentially that the identical objects should have the highest possible similarity. So if v is the vector x, or the vector v, and if you're applying the kernel to v itself, this should never come up to be negative, which means that the k should be such that, and again, this is essentially eigen decomposition, the eigenvalues should all be greater than 1. We'll see examples of this in a minute. So you can't have an inconsistent kernel where if two vectors are pointing in the same direction, like x and z, the kernel for x and z should never return something negative, which makes sense, because that in that way it would be inverting the similarity, so to speak. We don't want that. If you think of it as the kernel as a new space, if you do that, another way of looking at it is that you would be tearing the space, ripping the space, if that was the case. So Mercer's theorem, and essentially kernel functions that fit this idea are called Mercer kernels. have very kind of well-behaved properties, in that if you can show that your kernel, whatever you're using, is a Mercer kernel, you can basically plug it in without worrying in the place of any dot product. So Mercer's theorem basically says it's necessary and sufficient. So when you get these, it's both, you have to have all these rules correct, plus it's enough for this to be a Mercer kernel. For any function that the corresponding kernel matrix, remember the matrix you build from the inputs, has to be symmetric, like we said, and positive semi-definite. In other words, you shouldn't have any two constants Ci and Cj, such that when Ci and Cj are greater than 0, if you kind of multiply Ci times Cj times a cell of the matrix and add them all up, the total should come up to be greater than 0. This is a way of kind of, if you have a small matrix, a way of evaluating whether your kernel matrix is a Mercer kernel. Otherwise, if it's a large matrix, then you'll have to plug it into a computer and calculate the eigenvalues. That would be much more efficient to do. So whenever you have a Mercer kernel, you can use it for what we call the kernel trick, essentially exchanging the dot product in any clustering or classification algorithm with your kernel, so that you get a new space where what didn't used to be linearly separable is now linearly separable. And only a Mercer kernel is guaranteed to work in all cases when using a Mercer kernel trick. Certain cases when you don't have a kernel that's positive semi-definite might work, but essentially you're risking the mathematical robustness of it. Okay, so here's a few examples. When you look at this, you think this is a Mercer kernel. So at first glance, obviously it's symmetric, so we have that. And it turns out you can do this by yourself. For this matrix, you can't find any constants, C1, C2, C3, that are greater than 0, such that if you multiply these by those constants, the total sum of the matrix will be less than 0. So if just to see how this works, if let's say if all of them are 1s, this is basically the sum of the matrix, which is 1, 2, 3, plus 2 halves, that's 4, plus 1.2, 5.2, plus 0.6 more, 5.8. So there's really no way to have three constants in this case, such that you'll be able to have a negative sum on this matrix. So you have to find these Ci's and Cj's, and they should be greater than 0. Obviously, if you make them all 0, it doesn't matter what the matrix is, it will always come up to be 0, so that's cheating. These have to be greater than 0, but they can be any value that is not 0. Sorry, by the way, these don't have to be greater than 0, they have to be non-zero. Okay, so here's another example. So this first one was it is a Mercer kernel. In this one, you can see that we have a certain case where it's basically the same matrix, but these values are kind of higher, which means if you make C2 a rather large negative number, you can actually make this matrix inverting, which is exactly what we don't want. So this is not the matrix for an Mercer kernel, although it is symmetric. So for example, if you try 1, -1, and 1, then you have a problem, because essentially this is one these 2.5s will become negative 2.5, and the sum of the matrix will be negative, meaning it would, for a certain vector, it will actually invert the vector, which you don't want. And like I said, this is just to give you the intuition. A very kind of messy rule of thumb that I've come to use is, when you look at the matrix, if generally on a row, if some value is larger than the diagonal, then that's a bad sign. Okay, so you can use that as a rule of thumb. It's not by no means mathematically rigorous, but I mean, that's something I use. So if we get back to PCA, remember that finally when we derived PCA, we found out that the principal vectors, the principal components, were given by this matrix W, which was the matrix of vectors, each one being one principal component with the corresponding eigenvalue, lambda being the value which shows which principal component it is. So the highest principal component, the highest lambda, gave you the first principal component, the second principal component, and so on and so forth. Notice that essentially what you're having here is the rotations, the principal component rotations, times the covariance matrix. And remember that we said that the covariance matrix was essentially the centered data matrix times itself, the transpose of the centered data matrix multiplied with itself. Centered meaning, we subtracted the means of each dimension from that dimension. So when you look at the average of the matrix, it was 0. So this multiplication of the matrix with itself is essentially taking all possible inputs. If your data matrix X is sorry, my pen doesn't work again. Okay, if your data matrix X are your data points, right? So your first example, second example, etc., and the different features. Essentially, what you're doing when you're multiplying this matrix with itself is you're taking each data point and calculating the pairwise dot products of that point with each other point. Yeah. So essentially, this covariance matrix is actually the matrix of dot products of each of your points, which is by definition, it's a kernel matrix. The kernel function being the dot product of the vectors that make up your data, and the kernel matrix is the covariance matrix then, which means we could possibly, instead of if you're using covariance matrix, you're essentially using the kernel xy x dot y. Then the question becomes, why can't I use some other kernel here? So if I say, for example, kernel xy, I'll use the say the radial basis function kernel, right? X minus y squared and then 2 sigma. And again, the covariance matrix, as we know, is symmetric and positive semi-definite, and any Mercer kernel we use is symmetric positive, symmetric semi-positive, semi-positive definite, which means technically I can plug in any kernel I create instead of the covariance matrix in PCA and get a new and improved PCA. And that's exactly what it is. Instead of using the covariance matrix, you use your kernel matrix, which actually gives you PCA on this new space that's defined by your kernel, which could be kind of anything that fits the Mercer mold. This is what we call, for PCA and for other things, this is what we call the kernel trick. So you're essentially using a linear method, a linear classifier, or a linear dimensionality reduction technique like PCA with potentially nonlinear data. So here's what would happen. For example, if I had these points, let's say 3 groups of points arranged in a two-dimensional space like this. As you can imagine, if you ran a normal PCA on this, it wouldn't find any meaningful principal components because the variance is essentially the same in every direction. So it basically take a very minor difference, and that would be the first principal components and so on and so forth. So the eigenvalues would be very close to each other. However, if we use, for example, the RBF kernel that we saw before, you can actually get much better results. The RBF kernel, by the way, this form of the RBF kernel is called the Gaussian kernel because you're using, essentially you're naming it the Gaussian kernel because you're defining it in terms of standard deviation or variance, sigma. The true RBF kernel is generally written like this, e to the power of minus gamma x minus y squared. And this gamma, in this case, in the special case of the Gaussian kernel, gamma is 1 over 2 sigma squared, 1 over twice the variance. So it fits the Gaussian PDF. But I mean, you can use essentially any gamma here. Usually we tend to use the 1 over 2 sigma squared because you can sometimes define sigma from other sources. So you might have an idea of the standard deviation of your data in a certain space. Therefore, you tune sigma to that. And what the RBF kernel does is, like we said, it's no longer looking at the positions of each point because the position is now in an infinite dimensional space. It's technically what we call a Hilbert space, where only the minimum you need to define is the inner product, or in our case, a dot product. And actually, for any space of measures, that's the only thing you need to have. So if you have the dot products of all your points in the space, you can calculate the similarities between them. And if you want to localize them, you can always take the dot product of that point to some basis vector that you want, because when you think about it, any vector is defined 2, 3, 4 by its coordinates, and these coordinates are actually its dot products to each one of the basis vectors, right? So this vector is actually, if it's in three-dimensional space, there you have the x coordinate, the y coordinate, excuse me, the x coordinate, the y coordinate, and the z coordinate. And each one of these coordinate systems at the origin is defined by one unit vector that we call the basis vector. So the first one for the x coordinate is 1, 0, 0. Second one is the z coordinate is 0, 0, 1, and the y coordinate could be 0, 1, 0. And you see that when you take the dot product of the y basis vector with your own vector, you get 3. If you take the dot product with the x basis vector, you get 2, and so on and so forth. So essentially what we define as coordinates are actually dot products against the basis vectors. So once you define what a dot product is in a space, you have defined the space. You don't actually have to know all the basis vectors. So in this case, if you define it like this, as an RBF kernel or Gaussian kernel, essentially your space is no longer Euclidean. It's what we'll call a Hilbert space. So Euclidean is a special case of the Hilbert space, and in that space, uh, depending on the size of sigma, this creates a small hyperbole around an instance. So if I'm trying to figure out the similarity of x to z, and essentially there's this probability space, a probability hyperbole around x, and I look at what the probability of any other point z is in that spot. So if it's closer to x, the probability is higher, therefore the kernel is higher. If it's farther away, the similarity, therefore the kernel value diminishes very fast, and how fast it diminishes is based on sigma. So we generally do, the sigma is a free parameter that we need to set before we can use the kernel, and if that sigma is too large, then everything becomes similar because everything is within has a decent probability mass within each other's probability cloud. Or if you make the sigma very small, then there are very sharp probability distributions, and anything outside of that distribution is no longer similar. So you have to kind of tune it. There are several methods of doing this. We'll talk about that more when we get to SVM. There's rules of thumb, heuristics, or you can do a gain-based thing where you kind of try different sigmas and find out which performs best. Or you can already know the distribution of your data, the density of your data, and kind of estimate sigma from there. We'll skip that subject for now. We'll talk more about it when we get to support vector machines. Okay, so if you actually did use the RBF kernel, you would get a visualization like this. The first principal component, notice it actually separates the three classes very well. So essentially, you've taken this original two-dimensional data set, and that was not linearly separable, and you can drop it down into a single dimension where all the reds cluster here, all the blues cluster there, all the greens cluster here, so you can see the differences. And obviously this is between two-dimensional and one-dimensional. Dropping down to one-dimensional, what we generally do is drop down from however many dimensional to something like two-dimensional so we can actually see it with our eyes. There are other kind of mappings that you can use. One interesting one is what's called the isomap method, where you're actually not looking at the Euclidean distance between 2 points, but rather looking at the geodesic difference. So what you do here with the geodesic difference is you will take each point and find its closest neighbor, for example, and essentially say the distance between this and its closest member is, let's say, 3, and then from there you can find the closest member of each point, and you build a root graph, so to speak, between the different points. So it's as if you can't directly fly from one point to the other, you have to jump from point to point to get to where you're going. So the distance between, for example, this point A and B is no longer this distance, but the distance you have to jump through other points to get to that. So now if you can define that as a kernel, it allows you to visualize and map things that don't make sense when you use the Euclidean distance. So this is just an example of using something as a kernel that's not immediately obvious. And isomap actually is pretty it's been pretty useful for certain problems, but we'll see later on another example called stochastic neighbor embedding, which is kind of a local approach like this, localish approach, and we'll spend more time on it. For now, what I'm going to do is I'm going to jump back to Jupyter and show you examples of PCA, kernel PCA, and talk more about this through that medium, and then we'll come back and take a look at stochastic neighbor embedding.